All right, so after the token age checkpointing, we can actually take a look around the other functions in the token age token. And here we have, for example, implementation for ERC20, and it adds a bit more state. We keep state of the allowance of different addresses. Here we are using public override in order to make use of the fact that Solidity can actually generate a function from a mapping. So when you make a mapping public, it generates a function based on the type of the mapping. For example, this is a function that takes an address and another address and returns uint 256. And if we go into the interface, we can actually see that there is an allowance function that actually matches this signature, which is why we can override it. And we do something similar for total supply. Then we have this balance sub, for example, function, which just gets the last checkpoint of the stacks for that owner and returns the balance. We don't use like the last delegated balance checkpoint because that would actually return the total delegated balance for that owner. Then, for example, we have the transfer function, which calls this transfer internally. And all it does is, if the value is not 0, we first, actually the order again does not really matter, but we subtract from the from address and add to the to address. And internally, actually, we're working with 128-bit integers and not with the full size of the integer available in Ethereum. This is because in the checkpointing, so this should be 192 actually. This is something I would correct after the recording. But the idea is that here we are using 192 bit integers for the balance, so that the balance in the front time fit in one storage slot, and the token age goes into a second storage slot, and that way we're using only 2 storage slots for the balance checkpoint and not like 3. The delegate checkpoint uses again just 1 storage slot actually, because the address is 192. Actually, it is 160 bits, so it fits nicely with the time. And here the idea is that the token age, because it is balance multiplied by time, it actually needs to have the sum of balance and bits. So 256 actually those two numbers added. And while it's possible to fit the whole balance checkpoint in one storage slot, there are not enough bits for the time or the balance. And actually there 64 bits might seem a bit low for a time unit, but actually it's pretty fine with block numbers. Though I'm going to double check this after the recording, just in case I missed something. Going back here, we subtract from the from address, add to the to address, and emit the transfer. And it's important to emit the transfer even if the value is 0, because that is part of the ERC20 interface. And then we implement the transfer function, the transfer from, where we subtract from the allowance of the transferring address. So from the allowance for the message sender, and we can like double check that the allowance function has them named in that order. So it's first owner, then spender. Hence it is first owner, then spender here. And again, owner and spender. Here we're implementing a custom function for safe proof, which was taken from one of the issues on the Ethereum EEPS repository, which is basically the same as a normal approve, like increasing, like updating the allowance, but first making sure that the allowance matches a preset value, because otherwise there is a certain attack if somebody uses the allowance before it's updated. And that's about it. It's just an ERC20 implementation on top of the balance tags from token age checkpointing. And then we have an ERC1363 implementation on top of that. So the transfer and call implementation. And also we have to implement ERC165 for 1363 and say that we actually support this interface if anybody asks. Then we call like the transfer, we have a few helpers to call, like for a transfer received or approval received, and we just cast the recipient to the proper interface and make sure that the return value matches, and that's part of the 1363 interface. And that's about it. Ask any just ask any questions if you have them. It should be a pretty straightforward implementation of 1363. And finally, we have the weights implementation for iVoting weights. And actually, not all of those functions are implementing part of iVoting weights. A few of them are just helper view functions for like the own weight of a given address, which we take from the balance tags. Then we have the delegated balance, which we take from the delegated balance checkpoints, or the delegated balance at a given time. Or then from the voting weights interface, we have the waitf, or waitf at a given time, or the delegate of at a given time. And we also have a helper function for the delegate, current delegate. It's all view functions, which means that they cannot modify the state. And actually, they can be called freely on the client side because they never, when you call one of those functions, it never goes to the blockchain. And finally, we have the token age contract itself, where we all started this descent into madness. And it builds on top of the ERC1363 and the token age weights, but also adds a few things on its own. One is the delegate event and the delegate function, which basically calls the set delegate from the checkpointing earlier in order to allow people to change their delegate, because this is not part of the iVoting weights interface. And we also have a constructor which gets some initial owners and initial balances and just adds some balance to those owners and increases the total supply by those balances. And here the idea is that the total supply will never change because there is no mint function, which is why we're keeping track of the total supply directly in the constructor and never updating it afterwards. Though even if we add a mint function, we could change the total supply in which is stored in this variable. And I think that's about it for the token age token, this feat of engineering.